This lecture is in two parts. The first part is on UML, which you can think of as a notation to capture the results of analysis. So we'll cover UML first, and then we will go into analysis. First, structured analysis, and then agile analysis. To begin with, know that UML can be used in many ways, in three specific ways. The first is you can use UML as a sketch, which is as a way to document the results of a design or analysis or a system. Okay? The second way is you can use it as a construction document or a blueprint. That is, you can create a specification of a software system using UML, and then the implementer can take that blueprint and build the system from that blueprint. And the third way of using UML is as a programming language, which is you can create a specification for a system within UML, and that specification is in fact executable, which is either ideally the UML itself can be executed, or more realistically, from that UML, code can be generated, which can then be executed. Here is a use case captured in UML. I won't go into the details of the use case here because you've seen it before. UML simply incorporated the standard notation for use cases. In this particular diagram, we've shown the extends relationship between two use cases. The extends arrow is drawn from a use case X to a use case Y to indicate that the process X is a special case behavior of the same type as the more general process Y. You would use this in situations where your system has a number of use cases that all have some subtasks in common, but each one has something different about it that makes it impossible for you to just lump them all together into the same old use case. In this case, distribute transcripts and distribute fee schedules extends distribute information to students. The uses relationship in a use case or uses edge is drawn from a use case X to another use case Y to indicate that the process of doing X always involves doing Y at least once. So in this particular case, you can see that all those use cases are used by the use case that is pointing to it. Essentially, these are all components of the larger use case. This next diagram is a class diagram. So here are the things to look for on this class diagram. Look for the square boxes. These are classes. These represent classes. And the class diagram essentially shows the classes and the relationships between classes. One relationship, so the square boxes represent classes, and the lines with the arrows represent relationships. Note something about these relationships or the arrows, which is the cardinality attribute at the beginning and the end of the arrow. The cardinality basically indicates how many of the source of the arrow relates to how many of the target of the arrow, with the asterisk or star meaning 0 to infinity, and a number like 1, 2, 3, and so on indicating a specific number. So in this particular case, a particular order, a particular customer can have many orders, but each order can have only one customer. The arrow that connects the two is known as an association arrow. There are many kinds of associations. We'll just show in this diagram the highest level association, which is called nothing more than an association. Another thing that you will see in this diagram is something known as a constraint. So you will see something that says if order.customer.getCreditRating is poor, then order.isPrepaid must be true. So constraints are ways of saying something about the relationships between classes, actually instances of classes that cannot be said diagrammatically. So it's a programmatic way of saying something about the relationship that is not easily captured, or at least we haven't figured out a notation to capture it in a diagram. The next thing that you will see here, the next relationship that you will see here, is something known as a generalization relationship. And it's nothing more than an inheritance relationship. So in this particular case, customer is the superclass of customers, and then corporate customer and personal customer are subclasses of customer. This is known as this basically means that corporate customer and personal customer are related to customer through a generalization relationship. Also, within each class, you will see attributes. So quantity, so inside the order line class, you will see two attributes, quantity and price. Inside the customer class, you will see name and address. Inside the order class, you will see date received, is prepaid, number, and price. Note that in some cases, the types of the attributes are given. In some cases, the types of the attributes are not given. And the idea is, as you get deeper towards design or towards more specificity, you give the types of the attributes. When you're just trying to capture what that class is about, you can just list the attribute and not show the type because you haven't figured it out yet. The next thing that you will see within a class are operations. So inside corporate customer, you will see bill for month, and you will see remind. These are operations within corporate customer. Operations are also called messages. Now, when you're representing classes at a high level of detail, you might simply list the messages or operations. You might not show things like return types, parameters, and so on. As you get more specific, as you understand the system better, or as you're doing design, these operations will become functions within that class, and in that case, they will have actually parameters with types, return values, things like that. Sometimes you've got to pull an association into its own class, and the best reason for doing this is when the relationship has attributes that cannot be suitably placed in either of the two classes. So in this particular case, there is an attendance association that links person and meeting, and there is an attentiveness attribute that will represent the attentiveness of the person in the meeting. So you can see that this attentiveness attribute cannot be part of person because it has to be in the context of a meeting, and it cannot be in a meeting because it has to be in the context of a person. So the right place to put it is within the attendance class. So now here's an example of another diagram known as an object diagram. And the object diagram is used to show the relationships between specific objects in a system. So in this particular object diagram, you see an engineering organization whose location is Boston. That is the parent organization of two other organizations. One, the tools organization in Chicago, and the apps organization in Saba, wherever that is. And then two specific people, Don and John, who belong to the tools organization. Note once again that this is showing the relationships between specific instances or specific objects in a system. To see what the class diagram for this object diagram might look like, look in the right-hand bottom corner of this picture. Here you will see three classes: party, person, and organization. Person and organization are subclasses of party, and an organization can have more than zero or one parent, and that parent can be a party. Okay, so just to make sure you understand this, take a look at this class diagram and verify for yourself that the the object diagram that's shown here can be created by instantiating certain objects in this class diagram and then relating them together. Now let's look at the first of many diagrams intended to capture the dynamic behavior of a system. Okay? So this diagram is known as a sequence diagram. It shows interactions between objects in a system. In fact, it used to be called an object interaction diagram until it got renamed with a later version of UML to sequence diagram. Okay, so in this particular diagram, you see 4 objects: an order line, a product, and a customer interacting, presumably to fulfill an order. Okay. Um, Underneath each of those objects, you will see either a solid line or a dotted line interspersed with solid rectangles. These lines are known as the lifelines of that object. So the idea is that the lifeline indicates a timeline for that interaction. So interactions that take place earlier in the lifeline or higher up in the lifeline come before interactions that take place lower down in the lifeline. Okay. Then linking these lifelines together are messages. So calculate price is a message that is being received and being processed by an order. Get quantity and get product are messages being generated by an order and sent to an order line. A product, that dotted line coming back from an order line back to an order, is a return message. Get pricing details is a message that's going from an order all the way to a product, and so on. You will see different kinds of messages. So I already pointed out the return message. You will also see a message known as a self call or a self message. And here, an example of that is the calculate base price message that an order is making on itself, and calculate discounts is making on itself. Let's see what else. You'll also see rectangles. So you'll also see a rectangle that will go from beginning to end of a lifeline. So for example, the rectangle that is on an order. You will also see rectangles that have a beginning and an end. These are known as activations of that object. So for example, when a get quantity message is sent from an order to an order line object is activated, does something, and then potentially it could go to sleep. And then when the get product message comes from an order, it wakes up again and processes that message. A dual of a sequence diagram is what is known as a collaboration diagram. So here, you don't see objects lining up over the top and then lifelines that show the timeline of interactions. Here you see the objects placed spatially, and the messages going across arrows that connect from one object to the other, with the sequencing shown as numbers. So for example, in this particular collaboration diagram, calculate price, the message calculate price has a sequence number 1, so that's the first message. It generates two other messages, get quantity and get product, and we know that because they're numbered 1.1 and 1.2. The third message is get pricing details because it is numbered 1.3, followed by 2 other messages, calculate base price and calculate discounts, which have the numbers 1.4 and 1.5, and then calculate discounts generates a message called numbered 1.5.1, which is get discount info. The point to be made here is that a collaboration diagram contains identical information to a sequence diagram. In fact, you can convert from sequence diagrams to collaboration diagrams mechanically. It's just a different way of showing the interactions between objects. This diagram, known as a state diagram, is another diagram that can be used to capture the dynamic behavior of a system. In this particular case, it's trying to capture the dynamic behavior within a particular entity. So it's not talking about dynamic behavior in terms of interactions across entities such as objects, but it's trying to capture the dynamic behavior within a particular entity. So in this case, it's showing the dynamic behavior of an entity, say for example, the user interface component of a system. And it's basically, and further, this entity must be, the dynamic behavior of this entity must be representable as a state machine. So in this particular example, it's trying to capture the behavior of the user interface of a system. This user interface it can be represented as a state machine. The 3 states are when it is showing the update hardware window, when it is searching, and the third state is when it's displaying the new hardware window. And it shows how the transitions between these three states will take place for that user interface component. This slide shows an activity diagram. Activity diagrams are typically used for modeling at the process level, such as for modeling the logic captured by an entire use case or a set of use cases, or for modeling the detailed logic of a business rule. It's typically not used to model the behavior of a single method or a single object. It is usually used for modeling higher level things, once again, like processes. You might think of this as a flowchart, and a flowchart that is not often used to model the algorithm within a code, though it could be used for that. It's really used for modeling something at a higher level. So now let's look at a couple of diagrams that are used to model more specifics about a system. So, in an earlier diagram, you would have seen operations being listed within a class. At that time, we had not worried about parameters, types of parameters, return values, and so on. And in particular, we hadn't worried about whether that operation was a class level operation or a static operation or an object level operation. In this particular case, you see an example of an operation that is declared at a class level or a class scope. So get number is instance scope, and get next new number, because it's underlined, is considered a static operation. You would have also seen associations between classes. So in those earlier diagrams, the specifics of the association were not specified. So and there are two other relationships that are associations that refine the relationship between these two classes. The first is an aggregation relationship. So for example, if you have a club and you have people who are members of the club, the relationship between the two is stronger than just a general association, because a club contains the members. This could be modeled using an aggregation relationship, and you can see the notation for an aggregation relationship. You see an open diamond at the left and the arrow on the right that shows that the club contains the object on the left. The club contains the objects of the classes on the right, which is the person class. An even stronger relationship, stronger than aggregation, that is one of composition, where you have the similar membership kind of relationship, but the component, the member object, cannot exist outside of the containing object. So in this case, you have a object called polygon that contains points, and these points cannot exist outside of the polygon. Similarly, you have a circle which has a point at the center, and the composition relationship between circle and point essentially says, without the circle being there, the center, the point that is the center, cannot be there. So here's another advanced UML notation. Here we are, you saw class diagrams earlier. Here are those same class diagrams extended with an extended notation to show interfaces. Interaction overview diagrams are variants on activity diagrams that show an overview of the control flow. So the nodes within the diagrams are not normal activities that you would see in an activity diagram, but actually what are called frames. And within these frames, you can have the other diagrams that are used to capture dynamic behavior, such as sequence diagrams, collaboration or communication diagrams, state diagrams, and also additional interaction overview diagrams. This slide illustrates a UML notation known as swim lanes. So this is nothing more than a regular activity diagram, but the activity diagram has been partitioned into these parallel components known as swim lanes, where the activities that are performed by a particular actor all fall within one swim lane. So the stakeholder actor does the prioritize enterprise requirements and the describe enterprise requirements activities. The requirements analysis does the modeling, and then the enterprise architect does the modeling of the enterprise business architecture, supports project teams, and models the enterprise technical architecture. So once again, this is nothing more than a regular activity diagram, except that the diagram has been partitioned into these parallel lanes known as swim lanes that show which of the actors are doing which of the activities. A package diagram depicts the dependencies between different pieces that make up a model. So a package diagram can use packages containing use cases to show the functionality of different subsystems within a software system. Package diagrams can also use packages to represent the different layers of a software system to illustrate the layered architecture of a software system. So packages are just ways to collect other artifacts, use cases, class diagrams, code, etc., into components that can then, into components that sort of meet a single purpose. And then a package diagram then shows the relationships between these different packages. A deployment diagram shows how a system will be physically deployed in the hardware environment. Its purpose is to show where the different components of the system will physically run and how they will communicate with each other. So analysis is all about understanding. Understanding by separating the target of the analysis into its component parts and component aspects, understanding the static structure of the thing that you're analyzing. And note, I'm just saying thing for now, because I'll define thing later. Understanding the static structure, understanding the dynamic behavior of the thing that you're analyzing, and then capturing this understanding either in documents using English or using specialized notation such as UML, or capturing this understanding tacitly, that is, in shared understanding among the people working on the team. So when you're talking about a software system, what are the things that you might analyze? Well, the first thing you might analyze is the domain in which the software system is supposed to play a role in. Okay, so for example, if you were building an insurance application, you might analyze the insurance domain. What is insurance? Who are the customers? What are the different types of insurance? What are the different types of customers? How do they typically make their insurance buying decisions? What are the competitive forces playing within an insurance industry? All those different things about the domain. Okay, this is known as domain analysis. And actually, you did a good part of what falls under domain analysis in the business analysis part of your project. Okay, and the first module in this course was all about business analysis. Putting it in software engineering terms, it was all about domain analysis. Now, sometimes you will see a term known as a domain model. Well, in software engineering, it has become somewhat a tradition to capture the static structure of a domain using a UML model, and that model is called a domain model. Now, let's say that you analyze the domain and you identified a problem that you'd like to solve in that domain. Well, you might want to analyze that problem in some depth, and that analysis is called problem analysis. And then once you understood the problem, well, you might want to come up with a solution to solve that problem. Analyzing or understanding what that solution should be is known as solution analysis. Note here the progression from understanding to solving. So the domain analysis is understanding at a high level. The problem analysis is understanding at a lower level. The solution analysis is now trying to understand the solution. We don't quite call it design yet, because when you do solution analysis, what you're interested in is thinking of the system as a black box and considering how the actors in a system might solve the problem by interacting with the system at the system boundary. So solution analysis never goes beyond the system boundary, it just talks about how the users, the actors may interact with the system to solve the problem while staying at the boundary of the system. So how do you go about doing analysis? Well, the process is that you focus on the target of analysis and you focus on understanding, not focus on trying to solve any perceived problems in that domain. So when you do domain analysis, just focus on understanding the domain. Don't ask questions like, well, why don't you do this to solve it, other than to figure out why it's solved the way, why things are done the way they are done. Do not introduce design, in other words. And this directive is especially true when you start going down through the levels of analysis. So for example, when you're doing problem analysis, stay with doing analysis of the problem. Don't get into design. The reason is that if you get into design too soon, you might remove certain alternatives. You might not consider certain design alternatives that actually might be better. You might get too focused on a solution quickly and come up with a suboptimal solution. The second guideline is to be iterative and incremental. You cannot understand the whole domain or the whole problem or the whole solution at one chunk, because as you solve the problem and present that solution to users and to yourself, you will come up with you will actually understand better what else needs to be solved, or whether you've solved it correctly. So the goal is to be, just like with everything else in software engineering, be iterative and incremental. And also, by the way, be scenario driven. Okay. And what might be some techniques? So techniques are, you could reuse existing model like Porter's model, like your value chain analysis. There's also a model known as the component business model that we didn't discuss in class that can be used to understand a domain. Another step in the analysis process is to simply just create a categorized list of things in the domain, basically and then break that categorized list into nouns, which become candidate objects, and then the verbs, which become candidate responsibilities for these objects. Note that I'm taking you down an object-oriented path with respect to analysis. So when you extract your objects and you extract your verbs, you're extracting your objects and responsibilities. You're assigning responsibilities to objects. You're identifying relationships between objects. And once you start to understand the static structure, you document that in most likely a class model or an object model. Okay, and then as you start understanding the dynamic structure, the dynamic behavior of the system that you're analyzing, when you start figuring out how things interact in that system, then you would capture that using diagrams specializing in dynamic behavior, such as the UML sequence diagrams, collaboration diagrams, activity diagrams, and so on. There is also a technique known as the CRC card technique for doing analysis, and essentially it's a method for socializing the process of analysis. So what I mean by that is, analysis is a group activity. You would sit together in a room with the different stakeholders, and you would come to a common understanding of the system. The CRC card process is a systematic way of coming to a common understanding of the system using class, responsibility, collaboration cards. It's an object-oriented way of doing the analysis process interactively. So let's list the work products for analysis that I'll be expecting you to create as part of your project, and also that I'll be expecting you to understand. There are four of them: analysis guidelines, domain analysis, problem analysis, and solution analysis. So they're just analysis of the, the, the problem and the solution at different levels of detail. So the domain analysis is at the highest level. The problem analysis, like I said, is at the next level. And solution analysis is how that problem might be solved, but staying at the interface of the system. And you can see guidelines on the slide that talk about how to do this. So for the domain analysis, start with part one of the project, which was your business analysis. Create a domain model using an object diagram. For the problem analysis, start with the problem statement. Create an object model to describe the problem and use, explain problem scenarios using sequence, collaboration, or activity or state diagrams. So remember what we're asking for here. We're asking you to detail the problem scenarios, the problems that you're hoping to solve with the solution, not the solution itself, okay? So for example, if you've come up with an application that improves the productivity of the engineers in your company, well, in problem analysis, you're trying to understand the problems with productivity, the miscommunications, the inefficiencies, things like that the engineers are having. And then in the solution analysis, you are trying to describe a solution of how those engineers may work with a system in a way that the problems that they were previously encountering will no longer be encountered. So here are some notes on what you might put in your analysis guidelines work products. And remember, these analysis guidelines is like your intended development process, like your part two of the project, except focusing on analysis. So for the other pieces of other analysis work products, you're essentially following the process you describe in the analysis guidelines. So if you notice in the previous slides, I've asked you to do domain, problem, and solution analysis. And in each case, I've asked you to identify scenarios. Well, scenarios are the first step towards identifying the dynamic behavior of a system. So that's what scenarios are all about. They are work products used to capture the dynamic behavior. Well, so I'm just going to give you a short note on solution scenarios, but you should think of other scenarios, problem scenarios and domain scenarios as sort of similar. Well, a solution scenario is an elaboration of a use case. So in other words, you're providing more detail about a use case. And you can think of a scenario as describing one path through a use case. Remember, once again, I'm describing a solution scenario as an elaboration of one path through a use case. And actually, when you describe your solution, when you describe the requirements of your solution, there's a trade-off here. So you can either have use cases at the scenario level, in other words, quite detailed, or use cases that collects groups of scenarios. And it's really kind of up to you. You have to sort of make sense not to leave out too much detail or put in too much detail. So now let's talk once again about solution scenarios. So you take a scenario, which is one path through the use case. So the first component of a scenario is the use case itself. And then the second and third components of a scenario are what we call assumptions and what we call outcomes. So let's take just for grins, a login use case. So user logs into system. There are at least three scenarios that I see here. One is user successfully logs in by putting in a user ID and password. Second one might be user is unable to successfully log in because his password is incorrect. And the third scenario might be the user is unable to log in because his user ID does not exist, okay? So in each case, the difference between these three scenarios is the assumption. In the first scenario, the assumption is the user has the right user ID and password. In the second scenario, the user has the right user ID, but an incorrect password. In the third scenario, the user ID does not exist, okay? Now, The outcome in each case is also different. The outcome is, in the first case, is the user successfully logs in. In the second, it's the user unsuccessfully logs in, but the reason is different because of an incorrect password. So the scenario is different. And in the third scenario, the outcome is the user again unsuccessfully logs in, but that's because his user ID does not exist. Okay, so you can define scenarios, or you can identify scenarios by varying the assumptions going into a use case, and each different assumption will give you a different path through the use case, which will result in a different outcome. Okay, so how do you create scenarios? As I said before, identify all the different assumptions and outcomes in the use case. Um, and techniques include, talking to domain experts, looking at similar examples. So if you're building a reservation system, look at other reservation systems. If you're building some kind of dispensing device, it could be a Pez dispenser, well, look at an ATM example. Okay, review the problem statement, walk through case studies or storyboards. Basically, just look at all the different ways the actors might interact with the system for a particular use case, and you'll be able to identify the scenarios. For more information, look at the reference from the IBM book. This slide provides some guidelines on sequence diagrams. Once again, as with scenarios, note that we are using sequence diagrams to document dynamic behavior at any level of analysis, domain, problem, and solution. Okay, and it's a graphical representation of a scenario. Okay, it doesn't have to be a one-on-one relationship between a sequence diagram and a scenario. You can use a sequence diagram to describe multiple scenarios, all grouped into one sequence diagram, or you can explore only the major scenarios and document them, capture them using sequence diagrams. Now, the interesting thing about a sequence diagram is that it can be used to discover or validate responsibilities for objects. So for example, let's say you did an object model to capture the static structure, and then generalized it into a class model, and you identified what attributes and methods it might have, or actually what data and what responsibilities or messages it needed to respond to. Okay, you can then take the dynamic behaviors within the system, the things that happen, the active things that happen within a system, and create scenarios out of them, and then create sequence diagrams that essentially interact with the same classes that you have in your object model or class model. And when you do that, when you take the dynamic behavior and start modeling that, you will start finding out that the classes or objects that you have need additional data or additional responsibilities. That's what we mean by saying we use the dynamic behavior, or the modeling of the dynamic behavior, which is the sequence diagrams, to discover or validate class responsibilities. Okay, you will identify, when you identify these class responsibilities, you will identify the messages that the object is supposed to respond to. You will also identify internal activities that that the object is supposed to take part in. So self calls and things like that. And you've seen a diagram of a sequence diagram before. So an example of a sequence diagram before. So you know what the components are: the object, the timeline, the messages, loops, returns, internal, and so on. So you've seen that. Keep in mind that when doing analysis, don't get into details such as types of parameters, or, data types of parameters, or even writing the messages as function calls. Just keep the messages in English. Feel free to annotate. Stay at user observable behavior, etc. And here are some notes on object models. So as I said before, when you create these object models, use the sequence diagrams to derive and validate this. Use UML notation. Components of your object model will be objects of certain classes, relationships among them, attributes and methods. One thing you will notice, or one thing you will find helpful, or one hint you'll find helpful, is that when you do analysis, start with an object model as opposed to the class model. This is because when you're doing analysis, you're trying to understand the problem. It's better to start with actual examples. So for example, if you're analyzing a university, you might come to OSU and analyze it as a specific example. And when you analyze it, you might document the departments within OSU, the colleges within OSU, which are all objects, and show the interactions between them, and then generalize from there to the class of universities and the class of departments. So when you document what happens at OSU, when you're talking about the specific department and college and university objects, what you're really creating is an object diagram. Yeah. Once you've completed that level of analysis, you're then going on to generalizing it, then you're creating a class diagram. So the first step in analysis is usually a object diagram or object model. Here's an example of a domain model. So it looks like it's the domain model of the buying process within a store. So you have an item in a store, you have registers in a store, you have um, you have a single sales line item that records the sale of an item. You have a sale that consists of multiple sales line items. You have a payment that you make for a sale. And you can see here the associations, attributes, domain objects, cardinalities, things like that. Essentially, I'm looking in this particular case, it looks like the analyst went into a store or is analyzing the retail store domain and is capturing these objects and their relationships in a domain model. And here's an example on a CRC card. So CRC cards are nothing more than 4x6 index cards. They're called class responsibility collaborator cards. And you're seeing here one side of the CRC card. So you see the name of the class name. You have responsibilities listed there, and you have collaborators listed on the right. Some CRC card techniques allow you to list collaborators on the other side as well, or you might list the class name and the collaborators here and the responsibilities on the other side. It's all up to you. But basically, the idea is you're capturing objects and classes on 4x6 index cards. So far, you looked at structure analysis, and here's a short note on agile analysis. And basically, the only thing to remember is agile analysis is mostly about values and practices, not so much about techniques. So on this slide are listed all the values and practices around agile analysis. So analysis is an integral part of requirements definition. It's not a separate phase. You always do the modeling with others. You always model in small increments. Everybody owns the analysis. The goal of the analysis determines what model you create. There are no fixed set of work products you're supposed to create for agile analysis. You typically create several models in parallel. You use simple tools. And very importantly, you prove the analysis with code, not with more analysis. Everything is kept in a single source, so there is no overlap of information. You display everything publicly, and connected with modeling with others is that you get active stakeholder involvement. That means you get your users, their bosses, other people who are stakeholders, the sponsor, etc., involved in the analysis so that you can understand the domain and the problem and the potential solution in the most comprehensive way by taking advantage of the tacit knowledge of people. And this slide is here to make the point that any of the work products that you have for structured modeling or structured analysis, you can use for agile analysis and agile modeling. So here's a use case diagram. You've seen those before, drawn in a very nice way, probably using a tool. Well, if you did agile modeling, you'd probably just hand write on a whiteboard and take a picture of it.